In a previous lecture, we have seen the law of conservation of the linear momentum, angular momentum, and the work energy theorem for the single particle. Now we are going to study the dynamics of the system of the particles. So for the system of the particles, we must know that because the system of the particles is applicable in a day-to-day life. In a day-to-day life, we are not dealing with a single particle which is moving from one position to the another position, but we are dealing with the system of the particles. So it is more at the applicable level. Therefore, we have to study the dynamics of the system of the particles. Now, for this system of the particles, we must know few things like a system is made up of a number of particles, and let M or the capital M be the total mass of the system. I will write it as a total mass of the system. Okay, now this total mass is made up of some small particles. Suppose this is a block. So this metallic block is made up of very small particles, and let me call this each particle as M1, M2, M3 up to Mn. It means that n is the total number of particles. So m is the total mass and n is the total number of particles. This m1, m2, m3, these are the masses of the particle 1, 2 and 3, like this. Okay, if I want to select any particle randomly, I will call it as a ith particle. So this, it means that ith particle means any particle which I have selected for my experiments. Now the total mass of the system is given by m is equal to summation of this mi, where I runs from 1 to n. So what is the meaning of this? So the total mass of the system is the addition or the summation of all the particles, where total number of the particles is equal to n. We must know one more concept for the dynamics for the system of the particles, which is center of mass. So if I have any coordinate system like x, y and z, and if I'm just taking a system of only two particles for our simplicity. So this is particle 1 and this is particle 2. The position vector of this particle 1 is r1 and position vector of this particle is r2. Okay, so suppose there is some another point which is here, and let capital R be the position vector of this particle. I will write here capital R, actually it should be here. So capital R be the position vector of this particle. So the center of mass is defined as the point where the whole mass of the body is supposed to be concentrated. So if you take any body, suppose this is a body, so there is some point in this body on which if I hold on, so it will remain steady. So that point is called as the center of the mass of the body, and the center of the mass of the body is defined as, so this R is equal to m1 r1 plus m2 r2 upon this m1 plus m2. We are considering it for only two particles, but in day-to-day life we are not dealing with the body which is having only two particles. So suppose this is the body which we are dealing in a day-to-day life. So for that, R could be given by, so this m1 r1 plus m2 r2 plus up to mn rn upon m1 plus m2 up to rn, which can be written as 1 upon m, and we know that this m1 r1 plus m2 r2, this is nothing but a summation of mi ri, where I is running from 1 to n. So So this is summation of MIRI, where I is running from 1 to n. So that can be given as M into capital R. So this is the expression which we are using everywhere in the dynamics of the system of the particles. Summation of MIRI is equal to M into capital R, where R is the position vector of the center of the mass. Now let us see conservation of linear momentum for system of particles. If there is a system which consists of n number of particles, so this system will have two types of forces. First, which we are applying externally, which we call it as F external, and there is also internal force which is due to the interaction between the particles. There is internal force due to the interaction between the two particles. Suppose this is particle I, and let me call this particle as a J. So according to the Newton's third law, whenever this I particle applies force on this jth particle, the exactly equivalent opposite force is applied by the jth particle on the ith particle. So I can write this Fij. This is a force applied on the ith particle by the jth particle, which is equal to Fj into I. So which is a force applied by the jth particle on the ith particle. So the internal interaction forces are exactly equal and opposite to each other. So whenever there is a body which is moving from one place to another place, two types of the forces are applying on it. So it is F external plus this F internal. So this is the total force on any system of the particles. Now according to the Newton's second law, if I take any particle, so this total force on that ith particle can be given by F external, Fi external plus Fi internal. We are checking it only for one particle. So I have considered one particle as I. So total force acting on this ith particle will be force externally applied on the ith particle plus force applied internally due to the other particles on the I. So according to the Newton's second law, so this F total can be given as dpi upon dt. So this dpi upon dt can be also written as d by dt of mivi, where mi is the mass of that ith particle and vi is the velocity of that particle, which can be also written as d by dt of mi into, let me write it in a form of a radius, so it is the displacement dri upon dt. So this dpi upon dt can be also written as m into d upon dt square. Let me keep this m inside only, mi ri square, d by dt of mi ri. And we know that this if this is a condition for the one particle, so if I take the total force on the whole system, so that total force can be given by, this is a force on the ith particle. If I want to calculate the total force on this total system, I can take summation of this Fi, which is equal to summation of d by dt square of mi ri, or I will also write it as a d by dt square of summation of mi ri, and this summation of mi ri is nothing but d by dt square of m into this r, where m is the total mass of the system and r is the position vector of the center of the mass. So this Fi is also written as F external plus F internal. So in this also, so this F internal, as there is an interaction between each and every particle, and each and every particle is applying the equal and opposite forces on each other. So this Fij plus Fji will become equal to 0. So there is no internal, so the total internal interaction force will become 0, and we can write it as a F external is equal to d by dt square should be there, mr, and this is nothing but dpi upon dt, not I, dp upon dt. So this F external is dp upon dt. Now which says that, so this external force applied when it is a 0, then rate of change of momentum will be also 0. Okay. This is a law of conservation of the linear momentum. So when this dp upon dt is a 0, which means that this p is constant and the linear momentum of the system of the particles is constant. When the external applied force is 0, then dp upon dt is 0. When this dp upon dt is 0, which means that this p is constant or p is a constant. So the law of conservation of the linear momentum says that when external force applied on a system of the particles is 0, then linear momentum is conserved.